Hello and welcome to our presentation on memory management in Mac OS. I'm Sidesh Mahatre, and in order of appearance, presenting alongside me are Taylor Murray, Gabriel Norman, and Fahim Patel. I will be going over the objectives of our research, as well as touching on some key concepts that will give you some context for the later parts of the presentation. Here are the objectives of our research. Under background, we have Taylor going over some key topics including about the Mac OS, layers of the Mac OS, the virtual memory, and the UPLs. You'll learn more about this later in the presentation. And then we have the technical overview, where Gabriel has gone over reference counting, reference cycles, and Fahim has gone over memory paging, page lists, and paging in versus paging out. Now for some key concepts of this presentation. Let's start off with the basics. What is an OS? This is something you might be asking yourself right now. If you haven't been paying attention to lectures, an OS is basically the software program that's necessary and required to manage and operating a computing device. So you have all these different pieces of hardware that make up your computer. You need something to manage them and run them. That's where the OS comes in. There's many different types of OS you can choose from, like Windows, Mac, Android, Linux, whatever you want. The two most common are Windows and Mac, and today we'll be talking about Mac, Apple's Mac OS. Now, another question you might be asking is, what is Mac OS? Well, it's quite simple. Apple's Mac OS is the counterpart to Windows, like Microsoft's Windows OS. And it's basically, Mac OS is the desktop OS, right? So it's for all the iMacs, the MacBooks and stuff. And then they also have their infamous iOS, which is what runs on iPhones. So that's the difference between the two. iOS is for iPhones, like mobile stuff, like iPad, iPhone. And Mac OS is the desktop operating system that runs on the Macintosh computers. Now, another question, since this presentation is on the Mac OS memory management, I'd be asking, what is memory management, right? Memory management, it's pretty simple. It's pretty straightforward. Anyway, memory management is the process of controlling and coordinating computer memory, assigning portions known as blocks to various running programs to optimize the overall performance of the system.
Now we're on to the background of Mac OS. Some things Mac OS can do well and is known for are kernel programming, multitasking, and its file system. Starting off with kernel programming, the kernel is the heart of Mac OS X. It allocates computer resources and scheduling jobs, and this is able to ensure that each job gets a fair share of resources and access to the CPU and/or CD-ROM storage. The kernel also controls storage and printer management. It allows programmers to easily interact with an array of devices through its use of system calls. Multitasking means Mac OS allows for up to 100 users to concurrently use the system, each of which are running a different set of programs. These processes are able to communicate with each other whilst remaining entirely separate. Additionally, the per-user cost of the computer is lower when being used by many people, as no single user can hog the system resources. Mac OS is able to provide a structured and secure file system. All files are stored in a hierarchical system, meaning each folder is a subfolder of its parent. Mac OS consists of 5 main layers. Each of these layers builds on top of each other in order to handle more sophisticated tasks. The lower levels handle more specialized tasks rather than the more broad applications that can be handled by Cocoa. Layer 3, or the core services layer, is our focus here, as it's where memory management takes place. The core services layer is responsible for implementing most low-level features. These features are included in the core foundation framework, which is essential as the foundation framework is built off of for higher-level features. Cocoa uses the framework and applications kit to implement various services, including memory management. Moving on to virtual memory for Mac OS, it's a descendant of Mac VM. The idea of it is for physical memory to be a cache for virtual memory. These VM objects are cached as RAM. Each page is then represented in a given address space by a map entry. Next, we're covering shadow objects, and they come to be when a virtual memory object is duplicated. These shadow objects are initially empty, but as a page is modified, the contents of the parent object get copied into it. For data to be read, the system tries to read from a shadow object first, but if one doesn't exist, it will then default to using the original parent copy. UPLs are a data structure that are used for communicating with virtual memory. They can be used multiple ways for memory manipulation. Some examples include changing page behavior, such as for caching, mapping, or permissions. They can also be used for pushing and pulling data from virtual memory objects. The life cycle of a UPL only consists of 3 steps. First, it's created based off of a VM object. It's then modified in some way. And then lastly, those changes are either committed or aborted.
Okay, so we'll now look at a technical overview of how Mac OS handles the garbage collection side of memory management. The methodology that Apple uses in both Mac OS and iOS operating systems is known as automatic reference counting. When an object is created by the OS, automatic reference counting allocates a portion of the memory to hold the object's information. It also frees occupied memory held by object instances after they've served their purpose and must be disposed of to free up memory. So in order to avoid the algorithm from disposing of an instance that is currently in use, and to know which objects to delete, automatic reference counting recursively goes through all the objects, and it looks to see how many references exist to constants, variables, and properties in memory. The default reference type is known as a strong reference type, and it's used by the algorithm to prevent an object's deletion. So object reference counting assigns a property to each class, and it's called the reference counter. If it finds a strong reference, the counter is increased. If one's removed, it's decreased. If it ever goes below 0, the object will be disposed of, and if it is above 0, it will never be disposed of. So this creates a major problem because, as you can see, you can create an object that references a property in another object, and that object can reference a property in the other object, and this creates a situation where these objects will never be deleted no matter what. This is called a strong reference cycle, and if left unchecked can lead to very serious and compounding issues such as data leaks, which can grow and have serious repercussions down the line for the operating system. Automatic reference counting requires that when developers are creating applications to be used on the application layer, they utilize the weak reference keyword. The weak reference variable keyword implies that they will not be counted as a strong reference by the operating system. So when an object referencing them has all of its other strong references removed, the object will be deleted appropriately, and it will have its space freed in memory, and the variable pointer that it was referencing will be reduced to nil, so it won't be pointing to anything. Developers, if they want to customize the automatic reference counting to function like a different counting methodology, such as manual reference counting, they can also use the unsafe unretained keyword, which tells the Mac OS that the variable will also give a weak reference and allow referencing objects deletion, but the variable will not be set to nil upon the object's deletion. It will instead retain its place in memory and hold its pointer value. So as the name states, this can be very dangerous, as the variable can now become a dangling pointer that points to either nothing but deallocated memory, which can cause issues, or if the memory becomes repopulated, it can point to something totally different and cause a multitude of errors. So it's only to be used in very specific circumstances. But that's essentially how automatic reference counting functions.
Now that we've gone over how macOS deals with allocating memory chunks with automatic reference counting, I would like to go over how macOS deals with memory paging. In general, when talking about computer operating systems, memory paging is a memory management scheme by which a operating system stores and retrieves data from a secondary storage for use in main memory. In this case for macOS, how does it control the virtual memory that came from secondary storage such as a hard drive as opposed to main memory like RAM? And for reference, the virtual memory mentioned earlier is retrieved through the operating system getting data from secondary storage in fixed size blocks called pages. Mac OS implements memory management through the kernel, which maintains and queries 3 system-wide lists of physical memory pages. The first one being the active list, which contains pages that are currently mapped moved into memory and have been recently accessed by the operating system. The inactive list, which contains pages that are currently resident in physical memory but have not been used recently. These pages do contain valid data but may be removed from the memory at any time in order to free space. And lastly, the free list, which contains pages of physical memory that are not associated with any address space of VM object. These pages are available for immediate use by any process that needs them. macOS ensures that there's enough pages in the free list and will balance out the list as necessary. When the number of pages on the free list falls below a certain threshold, the pager will pull pages from the inactive list. If a page has been accessed recently, it is reactivated and placed into the active list. If an inactive page still contains valid data that can be used, macOS will attempt to page out its contents to a secondary storage device before it can be placed on the free list. If an inactive page has not been modified, it is stolen, meaning any current virtual mappings to it are destroyed, and then it is added to the free list. Once the free list size exceeds the target threshold, the pager rests. macOS also checks so when process explicitly frees memory, the OS will move the effective pages to the free list. As mentioned earlier, when the number of pages in the free list falls below a certain threshold, the kernel reclaims physical pages for the free list by swapping inactive pages out of memory. To do this, the kernel iterates through all resident pages in the active and inactive list, performing the following steps. If a page in the active list has not been recently touched, it is moved to the inactive list. If a page in the inactive list has not been recently touched, the kernel finds the page's VM object. On the side note, if the VM object has never been paged before, the kernel calls an initialization routine that creates and assigns a default pager object. The VM object's default pager attempts to write the page out to the backing store. For reference, a backing store is typically part of a secondary storage device, like a hard drive, that is used by a paging or swapping system to store information not currently in the main memory. Backing store is slower and cheaper than main memory. The backing store is mainly used in this case to store data from a page that's about to be purged to be repurposed as a free page. If the pager does succeed in paging out the object to the backing store, the kernel frees the physical memory occupied by the page and moves it from the inactive list to the free list. The final phase of macOS's memory management scheme is about moving pages into physical memory. A memory access fault indicates the paging process. This fault occurs when the code tries to access data at a virtual address that is not mapped to physical memory. There are two kinds of faults. A soft fault, which occurs when the page of the reference address is resident in physical memory but is not mapped to the address space of that specified process, or a hard fault, which occurs when the page of the reference address is not in physical memory but is swapped out to the backing store. This is what is typically known as a page fault. When any type of fault occurs, the kernel locates the map entry and the VM object for the access region. It will then go to the VM object's list of resident pages and it would decide to go look for it. If the desired page is in the list, the kernel generates a soft fault. If the page is not in the list, it generates a hard fault. For soft faults, the kernel maps the physical memory containing the pages to the virtual address space of the process. Those specific pages are then marked as active. As for hard faults, the VM object's pager finds a specified page in the backing store. The pager moves it into the physical memory and places it on the active list.